So yeah, at first some logistic things, because I told you last week, or I sent you also this message on Moodle, that you should pay to take a fee of $100. Yeah? So what I decided then, because you need fundraising. So, and it is, I don't know how much money there is, but it should be enough. So, and then I would suggest, that is your money here, because you did the fundraising. So, and then I decided that the fees can be paid from this money. This is okay for it. The fundraising was originally made for the excursion. So then we're taking their money from there. So, and those who have already paid to him, or to me, but he is not here today, then he will just give it back to you, So, and I will then I will ask Neil, I think Neil has the money, or who has this money? Yes. Okay, then I will tell him that he should hand out 3,800, and then the thing is paid. So, and actually we can also use this $10 from these funds for the entrance at this other hot spring here in Wittenberg. Yeah?
Yeah, so I took them, so we don't have to pay for the entrance, we will pay.
Okay, that is even better. So, okay, then we will pay this from that money. Then the whole thing is solved. So, and next Tuesday, we will not have the lab, but we will have made a class, So that we have that I'm through with the first part, what I like to show you, And all the movies on the documentation will be uploaded these days, So then you can also prepare yourself and start. So then the next thing that was the last practical, So, and can I just see, or can somebody show me what you have done? Yeah, but that is wrong. Yeah, this is also wrong. So, because I will just clarify it, you formed from the E function, you formed then the Ln function, for the rubidium strontium. Everybody did this, That is correct. So, but then the thing is, then you cannot just use this formula, putting some numbers in, because the numbers which I gave you, that was the 0.699, that is the age of the chondrite, and then you have the 0.7054, and that is the strontium 87 to strontium 86 ratio now. So over the whole period. So, and that means after the calculation using this lambda value, you should then get the whole age of the planet, and that is the about 4.5 billion years. So, but how does it work? That is actually nearly the same as you have done last year, and here we have the rubidium strontium. So, and that is actually from the system here, or from the technique, the same as you have done last year when you have calculated this triple point of the aluminosilicate. You remember this? So, and there, when you have calculated the triple point of the aluminosilicate, there you have these 3 lines, yeah? And all these three lines, or these 3 univariate curves, yeah? These was a linear function, yeah? Because all of them are straight. So in the linear function that you know from school, now we are going back to your school, that is y is mx plus b. So and later on in school you made f of x is mx plus b. Yes, everybody had this in school, yeah? So and when we are looking at this diagram, there we have this line, and this line is always the same, yeah? There you have here your value 0.699, and here you have your value 0.7245, something like this. So, but the slope of this line is always the same, and the age which you are calculating, I mean now when you are calculating the age of the whole planet, I mean the whole age, yes, when the planet was formed, then it should then plot somewhere here, there, yeah? So and if you are going from here to here, then it becomes younger and younger, yeah? So and then we have the rubidium strontium, and I showed you that is always like this, yeah? So here, if you have such a rubidium strontium ratio, then it is here, then your whole rock is younger. If it plots here, then it's a little bit older, yeah? So and then you have again 2 curves, 2 linear functions, yeah? You have this linear function and you have this linear function, yeah? So and therefore, you have just to use this one and put, at first you have to formulate it, what is the 87, 86 strontium value, and here you have this one, that is the initial one, that is this one today. So and then you can put in this in your function. So but the fact now that you have 2 curves, that means you might have 2 linear functions, yeah? That's the same as we have done in ES303 with the PT diagram, yeah? You are using 2 linear functions because you like to estimate the age here, yeah? So and then you are formulating, you have then y1 is mx plus b, and then the next one is y2 is mx plus b. So and then that is then maybe here also 1, 1, 1, and here we have 2, 2, 2. So and then you are putting these 2 functions together, then you can write and you can remove then the y. Then you have then m1 plus x1 plus b1 is m2 x2 plus b2. So and then you have just to form your reaction or your equation in such a way that you are calculating the rubidium strontium ratio, yeah? Yeah, because this one is unknown. These values you have, yeah? You have this one, that is the initial one, and that is the other one, yeah? So, but you must not only use this one or this one, you can also for yourself use something between, yeah? Then you get in a younger age, yeah? So, and therefore you have just to calculating here this crossing point, yeah? So, and if you have your crossing point, yeah, then you can go back to your actual function which you have formulated, the ln function, and there you can put in the rubidium strontium value, and then you get the age. So in there you can then play around, and you can then hand in this just somewhere after the field trip, yeah? That is a little bit of playing around, and at first I would suggest you are using this value, because then you know exactly what should come out. That is the 4.54 GA. Yep, that was this to bring a little bit light into the darkness. So then the next thing, that is at first for Randy, we don't have to write this letter because we will pay the fees from the funds for which you have done with the fundraising. Yeah? Okay. So then the next thing, who is Daisy Anisi? Ah, she. Yes, you wrote me these two mails, yeah, about the incompatible elements. So when that is so, it depends on the mineral. Nickel, for example, is compatible in an onion, yeah? So and therefore the distribution coefficient is then always changing. Because in other minerals, nickel is then incompatible, yeah? But for example, if you are looking for strontium or rubidium, rubidium, for example, remains then longer in the melt, and strontium is compatible in the legiplate, for example. So that changes then always. Is this answer so far? Okay, then we can continue. So now, last time I showed you something, or we did something about the growth of crystals, how fast they are growing, if you can, when you are forming bigger crystals, when you form smaller crystals, and. So and now we are doing something about phase diagrams. That is actually something which we have already done in 203. So and here we are doing actually only very simple phase diagrams. I mean the phase diagrams which we are using in engineer's petrology, they are in general much more easier to understand. Easier to understand as those in metamorphic metrology. So we have then one component systems, so and we have then, for example, one component system. These are PT diagrams. So then we have two component systems. And the two component system means that the pressure and the temperature must remain constant. Or you can variable one variable, and most of the time, that is the P or T, must be remain constant. Mostly the pressure is fixed. So why do you think why we are using, when we are doing the simple phase diagrams, why do you think in volcanology the pressure is always fixed for most of the time? That is, if we are looking for igneous rocks which are X2 CVAS, then the pressure is just 1 kilobar, yeah? Or 1 bar. So that is just an atmospheric pressure. So, and therefore we can then you make different, or you can show different diagrams or different features in diagrams. We have, or we can show the formation of different end members. So, and you know, for example, when you are looking at an olivine, then normally we have 2 end members. I mean, there are some lower end members around, but usually the most important end member, that is the forsterite and the firelight, and then between these end members you can then always show the mixtures, yeah? B, what is then B? We have eutectic systems. C, we have peritectic systems. And number D, what we have here, that is the peritectic system. So, and then we have 3 component systems. And that means the temperature T is also fixed. So that means the temperature T disappears as well. So then we are using now a binary system with an intermediate component. So now I'm making the diagram, and then we have some definitions. So you have seen this kind of diagrams before. Then we have here SiO2, and here we have Mg2SiO4. So then we are making this just in such a way and then so. And here something like this. Now we are making it not something like this. So we are making it something like this. Then we are going down here. And then we are going like this. And then we are going like this. So and now we have here different points. Here, for example, we have forsterite plus melt. So that's just, the SM is just the melt. So then we have here forsterite plus enstatite. So in the enstatite, then we have here the enstatite, that is then MgSiO3 . Then here I have here enstatite plus melt. And here we have the enstatite . Yes. Something like this, you have more of these diagrams in your ES303 documentations. So, and now we have to define different points here. So here, for example, I'm making a P, and the P, that is the peritectic, the peritecticum. That is the peritecticum. So then here we make in an E, that is then the eutecticum. Yep. So and here we are making something else. That is the thermal boundary. And here we have another eutecticum. And here that is the thermal boundary. So then we have here that on this side we have quartz. So in this side we do not have quartz. So what happens now at these different points? So first of all, the thermal boundary is always between two eutectic points. So in this thermal boundary, I have there some other sketches done then, but this thermal boundary, that is, for example, when we are running in the system between silica and here olivine, then the thermal boundary is this point. I told you that quartz and forsterite or quartz and olivine never occur together, yeah? So because if we are adding more and more silica, then we are forming from our forsterite, we are forming then an enstatite, yeah? So when that is thermal boundary, that is this boundary where it becomes separated. So for example, when you are checking your QAPF diagrams, you know, these are these diagrams. You remember them, yeah? Quartz, K-feldspar. Then you have here the fluids. And here you have the plagioclase. Then here on the upper side you have the silica saturated rocks. And this QAPF diagram can be used for volcanic rocks and for plutonic rocks, you know this, yeah? So, and if we are going, and here we have much more silica than here, and here this is then the thermal boundary. So that is this one. This is the thermal boundary. So that means these fluids, and you know what fluids by now is, that is nepheline, that is the calcite. they are formed very late because when we are getting in our system less and less silica, then you are forming these fluids because they contain less silica compared to the K-feldspar and compared to the plagioclase. Yeah? So the naphthalene that is then actually the sodium end member of this. The naphthalene is the sodium end member of this fluid, and the calcium is the potassium end member of this fluid. So, and there you have a thermal boundary, for example, in this system, because it can either go in this direction or either go in this direction. Yep. So, now the peritacticum. At the peritacticum, in congruent melting occurs. So what means now incongruent melting? That means we have here at this point Mg2SiO4, yes, that is the forsterite from here. So, and then when we are running around here, so for example, we have a melt composition from here, yes, here we have everywhere melt, then we are going down to our melting curve, we are running down here to the peritactic point. And from here in this stability field, we have forsterite plus melt. So if we are reaching this point here, and we would like to have the composition, we are going here, and then we are going here. So, and therefore, we are forming here MgSiO4, that is the forsterite, FO plus SiO2. So, and that is the silica activity, and the silica activity is with 1. Because if you have a silica activity of 1, then you would form quartz here, yeah? But you are not forming quartz here, because here we have the thermal boundary. Yeah? If something is, you must tell me this, yeah? Because when I was a student, it took for me also a while to check these things. So, and then we have here, we are forming then at the temperature Then we are forming here at the temperature, moment. I have written here 1587. 1587 degrees Celsius. Because we are dealing here with a pure forsterite in an experiment. We are forming then Mg2 Si2 06, and that is the N-star type, yeah? So when we are forming this N-star type, because when we are going from here to here, then we are getting more silica in the system, yeah? So and then we have this plus this gives this, and that is then that happens at the peritecticum, and that means incongruent melting, yeah? So and if we have if we have congruent melting, and that happens here at the eutecticum, yeah? Congruent melting occurs at the eutecticum. So, and that is here. So, how does this now work? There we are just starting with a different melt composition. That was this one now. Here we are starting, going down, going down, going down. That is maybe A. No, that is not A, because then that is then peritectic. Yes, here we have this. So, and if you have, if we are starting somewhere else, let us say here, then we are going from there to there. We are going down to the eutectic point, going here, going here. So and what happens here? We have here N-star type plus melt, yeah? Here we have only a melt. Here we are forming the first N-star type, but we have still N-star type plus melt. So, and if we are going then down here and coming to this place here, then we have N-star type without melt. So, and now it is clear what congruent melting means. That is Mg2 Si2O6 melt forms then at the temperature of 1500. Yes, this here is the temperature, yeah? T in degrees Celsius. So here we have higher temperature, we are going down with the temperature, and here we have then a temperature at 1500, exactly 1500. So and then we are making from our N-star type, which is here melt, we are making then 06, we are making then an N-star type solid. So that is just all, yeah? That is not difficult. So and then again to our thermal boundary. Then we are just starting here. No, not here, here. So and then you have to have just the opportunity to run here or to run here, yeah? Because on this side here, we have silica under saturation, that means we cannot form in parts. And on the other side, we have then here on this side, silica saturation. So are you done with this? So then just 2 points more. Increase or increasing in pressure leads to an increase of the melting point. So what means this? It means just if you are increasing the pressure, then you are increasing also the temperature when you creating your melt. So in the next thing, water decrease the melting point. So if you have a lot of water present, then you can create a melt at lower temperatures. So and if you are checking your ES303 documents, there I gave you 2 diagrams. where you can see how a dry granitic melt, or at which temperatures a dry granitic melt becomes formed or will be formed, and at which temperature a dry one. And the same diagram I gave you also for the basalts. So, then this chapter is finished. Next one. So what we have done by now, that is just some basics. So, but now we are coming to the rocks itself. And that is then the petrology of magma tides. So there we are dealing, or we have different melts / magmas. So, and that is because of different primary magmas or melts. So, and what is the primary magma or melt? That is the original parental magma. Yeah? So, and then the next difference from our melts, that is then called, is, now let us make it due to changes of the melt. Of the melt. So what means changes of the melt? That means when you have, or when you are creating somewhere below a melt, it doesn't matter if it is at the middle ocean ridge or somewhere else, in a subduction zone or whatever you want, then while your melt is rising up, it runs through certain rock units above. Yeah? So in these certain rock units, they become the molten, and therefore you are always changing the melt. Yeah? Chemical composition, we are doing this then later. So, or certain minerals are crystallizing from your melt, sinking to the bottom, then you are also changing the melt again. So you are changing the melt all the time. So then we have here something to physical conditions. So the physical conditions. So these different rocks, yeah? These different rocks are formed at different temperature, yeah? And the temperature, that is a physical condition, yeah? So, and there I have have some numbers for you. For example, if you are looking for the temperature, and we are looking now for a basalt. So when such a basalt is formed at temperature usually between 1100 and 1200 degrees Celsius, but sometimes also at temperatures of up to 1300 degrees Celsius. So that was when you are checking all these basalts, and in Koro you saw a lot of basalts that was quite hot. So now we are looking for komatites. So in such a komatite is formed, for example, between 1400 and 1600 degrees Celsius. So, but we do not have in Fiji komatites, but the next one which I presenting you, that is the andesite. And you saw by now a lot of andesites on every excursion. And these andesites, they are formed between 1000 and 1100 degrees Celsius. So why do you think is the andesite formed at lower temperatures compared to the basalt? I mean, we have those rocks here everywhere around. That is because the andesite has more silica. So if you are going always to the more and more undersaturated side, then these rocks are formed at higher temperatures. So and those which are formed at lower temperatures becoming then more and more enriched in silica. So now we are going to the silica-rich rocks. That is, for example, the phonolite. Phonolites you do not have here, but it is interesting to know why this rock is called phonolite. Because in former times, they have just cut some slides from phonolite, and if you are using it then like a drum or something like this, then it makes a nice sound, and therefore it is called a phonolite. It's not a joke, it's true. So when this phonolite is formed at 900 degrees till 1000 degrees Celsius. So and then we have the rhyolite, and you know the rhyolite. The rhyolite is chemically the counterpart from the granite, yeah? The rhyolite is just an extrusiva and the granite is an intrusiva. So that is then very silica rich, and there we are dealing with temperatures between 750 and 900 degrees Celsius, yeah? And the melt minimum is at about 750 degrees Celsius. So that is the temperature when they are formed, yeah? So can I remove this? So, but now another physical parameter, what do you think is could be the next physical parameter, which is very important? Yeah, the pressure, but it's something else. That's the viscosity. That is the viscosity. And that we are measuring in poise according to Stokes' law. So I don't know if you heard something about Stokes' law, but I think so in your physics class. So the viscosity. So if we are looking for the viscosity of water, then water has a viscosity of 10 point minus 2. It has a viscosity of 10 point minus 2, and now we are checking just the viscosity of a few rocks. So there in rocks we have a huge variation in the viscosity. So then let us just start with the basalt. The basalt or a basaltic melt has a viscosity from 10 powered by minus 2, that is the same like water, to 10 powered by minus 5. Even a basaltic melt is very liquid. It can be or is about here we have a v for the speed, yeah, that is a small v, is about 50 meters in an hour. Yeah, that is not too bad. So the andesite has a viscosity ranging between 10 power minus 6 to 10 power minus 7. So then we have as next as an example, we have the dust side. In the dust side has a viscosity of 10 power minus 10. And that is like, and now I need your help for the translation because I don't know how it is called in English. You know, in former times when they have closed an envelope, they had these rings, yeah? So in there they had some color on it. You know what I mean? So and then they closed it and it was like a stamp. How is it called? Okay, seal color. Yeah. So that is like 10 power minus 10, that is like seal color. So and last not least, the obsidian. The obsidian, you know, we have this guy somewhere here in the cupboard, yeah? The obsidian has then a viscosity of 10 power minus 11 to 10 power minus 12. And that is then at 800 degrees Celsius. I mean, the obsidian is actually quartz, and therefore it has then a higher viscosity. So can I remove this? So I told you, or we have just written it on the last page, that we have different primary magmas. So and now we will discuss how does this come. Yeah, there are different mechanisms why we have different primary magmas, because they are changing always their composition. So, and that is mainly caused by differentiation. So, and therefore, we have the liquid unmixing. So now we have to think about what means liquid unmixing. That means we have different components which are not going together. Yeah? So for example, sulfide. Yeah? So if you remember the core shed last year, then I told you, I don't know, but you found there some sulfides inside, pyrite and galenite and all these things. Yeah? So and these sulfides, they are forming certain minerals which are not coexistent with other minerals. So that means they are not in equilibrium. So I make here now just some points, and then I will show you later how it looks like in detail with the liquid unmixing. Yeah? So then, for example, the next thing here, we can make a 1 maybe, but it's up to you. Number 2, we have then magma mixing. So if we have magma mixing, I mean that is now easy to understand. We have at least 2 melts and they are mixing each other up. Yeah? We have at first one primary magma, then it comes in contact with another magma, and then you are forming, depending how many percentage you are putting of magma 2 in magma 1 or otherwise, or the other way around. So and then you are just changing the composition. Yeah? That is magma mixing. Yeah? That is the next point. Number 3. But as I told you, we will discuss this afterwards more in detail. The next point, that is number 3, and that is assimilation. Assimilation. So what means now assimilation? That means, for example, contamination with crustal material. So, and that is this, our melt runs then, for example, through the continental crust. So, and then you have the contamination with the crustal material. Therefore, you are changing then also always the composition. Yeah? So, and that is important. For the rare earth elements. So it depends the light rare earth elements, the heavy rare earth elements, and so on. And for the isotopes. So because isotopes, you know by now that is, for example, the strontium-87 to strontium-86, yeah? So, or the oxygen isotopes or whatever you want. So, and I mean, the isotopes in a more silica saturated rock is different from those to compare in a mantle rock, yeah? I showed you last time these diagrams, how the isotopes are changing. And that is also important for the isotopes of the Earth elements. So because you are using these isotopes, and I told you, you are using these isotopes to figure out about the melt evolution of your magma, or the evolution of your magma, yeah? So, but there we have a limiting factor. And the limiting factor, or limited factor, that is the temperature. So I mean, as soon as your magma or melt has the same temperature as the surrounding rock units, then there is not too much assimilation going on. So because if it has the same temperature as the surrounding rock units, then your melt becomes just stacked and start to crystallize, yeah, because it is not only the temperature, it's also the density, yeah. So that means the heat flux between the magma and the surrounding rock units if the heat flux between the magma and the surrounding rock units is too low, then assimilation processes are limited. So because you need a high heat flux or a high difference in heat to melt the surrounding rock units, yeah? So and if this is low, then nothing happens, yeah? Then number 4, that is the gas transport. So what means the gas transport? I mean, you know, in your melt you have a lot of volatiles. There is water, CO2, there is methane, there is nitrogen, and so on. So, and I mean, if you have a melt, then your gas has a much lower density, of course, and it tries to escape, yeah? So, and it goes always from the bottom to the top, yeah? It's rising always up, yeah? So, and if you have a gas transport, then we have mostly alkali transport. So, and if we have an alkali transport, then we are talking about alkali transport leads to an enrichment of alkali at the top of the magma chamber. So, and that looks then like this. Here we have such a chamber, yeah, you know by now, that's always this bone what I'm making here. So then you have here at the top you have the alkalis, and below you have the tolluids. So we will discuss this then also later. So, but that is tolluids. So, and of course, due to this gas transport, I mean alkali, these are the potassium and the sodium. So, and they are the light, they are very light, and they have only one electron in the outermost rim, and so you can easily transform them, yeah? So, and therefore you have more alkalis at the top of your chamber, and below you have the tolluids. So, and that is the reason when you are looking, for example, but we are doing this in details when we are talking then about the hotspots. If you are looking at the Hawaiian hotspot chain, yeah, So, and then they have different volcanoes on one row, yeah, you know this by now from ES306. And then they have this line of all these volcanoes on the what? On the Hawaiian chain. So, and these volcanoes are not only showing a variation in age, yeah, because the oldest one was formed at first, the youngest one was formed latest, yeah. So, and you know there is a plum beneath the oceanic crust. So, and from time to time, it's erupting while you are moving the oceanic crust above. So, and the oldest volcanoes from the Hawaiian chain, they consist of alkali rocks, where the youngest ones consist of toledic rocks. Yeah? So, and that is then caused by this gas transport, but we are doing this again when we are talking about the Hawaiian hotspot chain. So, then we have number 5. That is the Soret diffusion. So what means the Soret diffusion? Of course, it is written that is much more efficient as differentiation. So, and that is just the movement of component because due to the temperature gradient. So, but that we will also do then when we are doing this more in detail. So now I can remove this. And we are coming to 6. That is the fractionated crystallization. So, and that is crystallization and that is also then the residual melt. So, and that we have done now a couple of times, also in the ES301. You have a magma chamber, and this magma in this chamber is cooling down, and it's cooling down from outside to inside. So, and then at the rim you are forming very fine-grained rocks, which are cooling down very fast, yeah. So, and there you are forming then other minerals, which some other elements inside, and then you, at the end you have your residual melt, yeah? So, and you can start at the rim with a melt of with a basaltic melt. So you are starting here to crystallize at the rim. There you have then some fine-grained rocks, maybe of mafic composition. So, and then you are crystallizing from inside to outside. Here you have then some minerals are formed with sinking down. So, and here you have then your residual melt. So, and this residual melt can be then of granitic, even of granitic composition, yeah? But we have done this now a few times. So, and then I think we can finish for today.